Here you see a picture of Lebeg, the person who pioneered the theory of the Lebeg integral. In this video, we are going to study the most important theorem in Lebeg integration, Lebeg's dominated convergence theorem. In fact, it is this theorem that makes this integral the canonical integral in analysis. Apart from analysis, this theorem is extensively used in probability theory, usually to find out expectations. So, 25 years from now, if somebody asks you, what did you learn in your course on real analysis? The one thing you should never forget is Lebeg's dominated convergence theorem. It's going to be as relevant 25 years later as it is now. It's that important. Let's state the theorem. This is going to be an extension of the monotone convergence theorem that we have seen, except now we are not going to assume any good behavior about the sequences of function in terms of monotonicity, but rather we are going to assume that the pointwise limit of these functions exist. So that's one crucial difference. So let's state the theorem. Let Fn be Lebeg integral over the interval I. Assume first of all that Fn converges pointwise almost everywhere on I. We didn't have this first requirement in the monotone convergence theorem because we got the existence of a pointwise limit from monotonicity, rather from the fact that if you have an increasing monotone sequence of real numbers that is bounded above, it's automatically going to be convergent. So that sort of helped us get a limit function for free. But because we are not going to assume anything about monotonicity of the functions Fn, we have to assume that the pointwise limit exists. Number two, this is the crucial hypothesis, and the hypothesis that sort of lends the name dominated. There exists a function g from I to r, g is greater than or equal to 0, such that for all n we have mod fnx is less than or equal to g of x almost everywhere on I. So this function g, which is a non-negative, of course I must mention that g is in L of I, otherwise this whole thing is nonsensical. So we have this non-negative Lebeg integrable function g which dominates the functions Fn, and this g is independent of n, remember that. Okay, what is the conclusion? Then f is Lebeg integrable, and as you can expect, the integral of f is nothing but the limit of the integrals of Fn. So the hypotheses are that you have a sequence of Lebeg integrable functions that converge almost everywhere pointwise, and these functions are dominated by a single non-negative Lebeg integrable function. Then the conclusion is that the limit function is Lebeg integrable, and the integral of the limit is the limit of the integrals. Okay, so let's go on with the proof. Briefly speaking, there is nothing deep that's going to happen in this proof. We are just going to manipulate the sequence Fn, but the basic idea is to apply the monotone convergence theorem to get functions gn and capital Gn. Both of these functions will be Lebeg integrable. We have to cook up these functions such that this little gn is always less than or equal to Fn, and this is less than or equal to Gn. Of course, all this we need it to be true only almost everywhere. We want Gn less than or equal to Fn less than or equal to capital Gn, and we want Gn increasing to f almost everywhere, whereas capital Gn decreases to f almost everywhere. Okay, so let's assume for the time being that we have actually found out these functions gn, so little gn and capital Gn with the property that little gn is less than or equal to fn, less than or equal to capital Gn almost everywhere, and we have gn increasing to f almost everywhere and capital Gn decreasing to f almost everywhere. Okay, with this done, the result follows almost immediately, because you can integrate this entire expression, integrate this expression out. So you will get integral of gn over I is less than or equal to integral over I fn is less than or equal to integral over I capital Gn. Okay, but because this little gn, for instance, this little gn increases to f, this side sort of converges to integral over I of f by monotone convergence theorem. Because gn increases almost everywhere to f, it follows that integral of I gn must converge to integral of I f. In fact, as a consequence, we get f is in L of I. F is Lebeg integrable. This much we get. Of course, the middle side remains the same. Now, this capital Gn, this sequence decreases to f. When we established the monotone convergence theorem, we established it only for increasing sequences. But there is nothing special about increasing sequences. You can formulate and easily prove an analogous version of the monotone convergence theorem for decreasing sequences also. So once having done that, it will be easy to see that this converges to integral of I f as well. Okay, and you will have this inequality. So integral of I f is less than or equal to integral of I, of course, okay. I made a slight error. I said there is no change in the middle term, but there is a change. There is a limit n going to infinity. Okay, so we get integral of I f is less than or equal to limit n going to infinity, integral of I fn is less than or equal to integral over I f, which just shows that limit n going to infinity, integral of I fn is integral of I f. Okay, so this will finish the proof. So all we have to do is manufacture these functions little gn and capital Gn. I will manufacture the function capital Gn with the required properties. The little gn function will be can be easily produced by adopting the same procedure by replacing maximum by minimum in certain places. So let's see how to do this. What we do is we first define capital Gn1 to be maximum of f1x, f2x, comma dot 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 fnx. Okay, so Gn1 is a function from I to R. It's obtained by taking the maximum of the first n of the functions f1 of the sequence fn. You just take the first n of them and call that the maximum Gn1. Now Gn1 is obviously going to be Lebeg integrable because it is given by taking maximum of Lebeg integrable functions. So there is no issue there. Furthermore, you have integral of I Gn1. This is less than or equal to integral of I, the absolute value of Gn1. This is just a basic property of Lebeg integrable functions we have already seen. And this is less than or equal to integral of I g, where g is the function that dominates each one of the sequences, every element in the sequence fn. So this g, right? So because this Gn1 is just maximum of f1 to fn, and the absolute value of each one of these is dominated by g, we get this inequality from the basic properties of Lebeg integrals under ordering. Okay. So in particular, what we have is integral of I, G and 1, this set, you look at the, is bounded above. Okay, in fact it's bounded below also, bounded above and below also, because there is an absolute value here. It's going to be bounded below also. That will play a role a little bit into the future. Okay, anyway, this is bounded above, and clearly Gn1 is an increasing sequence. So everything is set. At this stage we can apply the monotone convergence theorem. Applying MCT, we conclude that Gn1 converges almost everywhere to a function G1 which is Lebeg integrable. Okay, and not only that, we have that the Lebeg integral of G1 is nothing but the limit n going to infinity of Lebeg integral of Gn1, which is less than or equal to Lebeg integral of G. Right? This follows from the inequality that we have here. In fact, from that same inequality, we can in fact conclude that integral of Ig, the negative, is less than or equal to integral of Ig1 is less than or equal to integral of Ig, because we had an absolute value here. So what we have got is, we have got this function G1 by monotone convergence theorem. We have got this function G1, and this G1 is Lebeg integrable, and it's dominated by integral of Ig, and I mean in absolute value it's dominated by the integral of G, in fact. Okay, now let's proceed with the proof. Let's see, analyze this function a bit more. Notice that G1 is how do you determine G1 of x? Well, what you're doing is you're taking maximum of f1 of x dot 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 fn of x, and then taking limit n going to infinity. Right? That's essentially what G1 of x is going to be. So whenever Gn1x converges to G of x, remember this convergence is only almost everywhere on I. Whenever this convergence happens, G1 of x, whenever Gn1 of x converges to G1 of x, we conclude that G1 of x is nothing but supremum of f1x, f2x, comma dot dot dot. Excellent. Okay. Now what we are going to do is we are going to manufacture G2, G3, G4 in an exactly similar way. We are going to define Gnrx to be the maximum, but starting from the rth sequence, frx, fr plus 1x, comma dot 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 fnx. Okay, and this is defined for all n greater than or equal to r. Okay, so we define this new sequence Gnrx defined for n greater than or equal to r by taking maximum of frx, fr plus 1x dot 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 fnx. Okay, clearly this sequence Gnr also increases. Exactly the same reason why Gn1 increases. You are taking maximum of more and more functions, so the value can only increase. And again by monotone convergence theorem, Gnr must converge almost everywhere to a function to a function gr which is Lebeg integrable, and we also have these inequalities. Minus integral over ig is less than or equal to integral over igr is less than integral over ig. Exactly like before. Excellent. Now observe exactly the same observation that we have here. Exactly the same observation we have here. We can write down that gr of x is nothing but the supremum of fr of x comma dot 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 all the way up to infinity whenever gnrx converges to grx. At those points where you have convergence, this grx, the value of that is nothing but the supremum of frx, and you frx fr plus 1x dot dot dot, the supremum of this set. Okay, so from that we see that frx is less than or equal to grx almost everywhere on I, because the sequence gnrx converges to grx almost everywhere. At those points of convergence we have this expression, and therefore we have this inequality. Okay, now this grx is going to as the notation suggests is going to be our required thing. We have to show that grx converges to the function f pointwise almost everywhere. First of all, grx is certainly a decreasing sequence. Why is grx a decreasing sequence? Well, by definition, you notice that the supremum that you're taking is over less and less number of functions as r increases, therefore it's a decreasing sequence. Now suppose x in I is chosen so that limit n going to infinity of fn of x is equal to f of x. Remember, the sequence fn itself does not converge everywhere to the function f. It converges only almost everywhere. What I am going to show is that at those points of convergence, we actually have that this sequence gnx also converges to f of x. Okay. Now, what is the meaning of limit n going to infinity fn x equal to fx? Well, fix epsilon greater than 0, then there exists n such that if small n is greater than n, then f of x minus epsilon is less than fn x is less than f of x plus epsilon. This is just the very definition of limit n going to infinity fn x equal to fx. Now that we have this, it's clear that if you take supremum of fn x, fn plus 1x, comma dot dot dot, you will have f of x plus epsilon is less than or equal to this, is less than or equal to f of x plus epsilon. In other words, we have f of x plus epsilon is less than or equal to gnx is less than or equal to f of x plus epsilon for all n greater than capital N. Okay, and this just shows that gnx converges to f of x. So what we have managed to show is that this sequence of functions gnx converges to f of x precisely at those points where fn x converges to f of x. Okay, what next? Well, we already observed that gn is a decreasing sequence. Gn is a decreasing sequence of Lebeg integrable functions. Okay, Furthermore, we also observed that integral of Ig is less than or equal to integral of Ign for all n. Okay. Now by monotone convergence theorem for decreasing sequences, you have to formulate and prove this. Formulate such a theorem and prove it also. It's not that hard. You can just adapt the proof of the increasing case, or just once you state the theorem, you can see how you can use the theorem for the increasing case to prove the decreasing case. Anyway, by the monotone convergence theorem for decreasing sequences, Gn converges. We already know Gn converges. We know that the limit of Gn, which we know to be f, this is Lebeg integrable, and we also have that Lebeg integral of f is nothing but limit n going to infinity of integral of I Gn. Okay. Now we already know by a construction that fn of x is less than or equal to Gn of x. In an analogous way, by considering g little g n1x to be by definition the minimum of f1x dot fnx, and g nrx for n greater than or equal to r to be minimum of frx dot fnx, and adapting the same argument, we get functions Gn which are Lebeg integrable, and Gn of x is less than or equal to f of x is less than or equal to capital Gn of x almost everywhere. Even this is just almost everywhere. Now the first part finishes the proof, the discussion in the beginning. Finishes the proof. So there is nothing really much happening in this proof. You just have to construct these sequences and play around with them for some time, and you will eventually get the result. In the next video, we shall see applications of both the monotone convergence theorem and the dominated convergence theorem, including a particularly interesting one about uniform convergence. This is a course on real analysis, and you have just watched the video on the Lebeg dominated convergence theorem.